Okay, let's see if we can understand how this MaxBin software is working. So, the paper I'm talking about is, let me highlight it here. And follow the link in my document and you will get to this paper. And we only focus on the methods here now, right? You can read the rest yourself if you are interested, but we focus on understanding the method. And here we have a drawing, an overview drawing, and so on. So I had some sort of points that I emphasized in this document of mine. So let's see if we can step through this together. So first of all, what type of information is used from each config? And if we go into the paper here, it says here, the MaxBin algorithm utilizes two different genomic features. First, tetranucleotide frequencies and scaffold coverage levels. Right? So these are actually the two pieces of information that is used here. And what does it actually mean? It means that, first of all, they talk about scaffolds in this paper, right? Scaffolds instead of contigs. We usually call them contigs, right? But think of it as the same thing. A scaffold is it's slightly sort of bigger than a contig. You glue the contigs together into scaffold, but usually we don't care about this difference, right? And very often, if you compare scaffolds and contigs, you will see they are very often quite the same. So whether I say contigs now or scaffolds, it means actually the same thing, right? Genomic sequences that we have assembled, right? So the first piece of information, or one piece of information, is the read coverage. And this is reasonable, right? Because we know that there are possibly many genomes in this metagenome, right? That's true. But all the contigs that come from the same genome should have the same coverage, simply because they come from the same genome, right? You can't have different coverages in the same genome. So that's not unreasonable that we try to use this piece of information. And this we can actually calculate, right? By mapping the reads to the contigs, and actually BAO-TIE2 that we have used for read mapping in this course is also what is used by this MaxBin software. So that's why we have to supply as input to MaxBin also the reads. Right? We have to, of course, supply the contigs. That's obvious, because the contigs is what we are going to bin or group, right? But we also have to supply the reads so that MaxBin can do this read mapping and then compute the average read coverage for each config. So we have looked at the read coverage computations before in module 5, I think, but now it's done per config, right? Not as per position like we did in module 5. We did it for every single position, but now we do it as an average for each config. And then, of course, the contigs that come out with more or less the same coverage are probably, or at least candidates for coming from the same genome, right? It's not a guarantee though, because two different genomes can easily have the same coverage. But if contigs have wildly different coverage, they cannot come from the same genome, at least. That's at least what we can say here now. The other piece of information is this, tetranucleotide frequencies. What is this? Well, tetranucleotide is simply another word for 4 mers. 4 mers, right? We have looked at k-mers, and here they use k equals to 4. And that's a little bit strange. You might say, why 4? First of all, we are used to k values being odd numbers, not even numbers. And why is this short? Why should they be so short, right? Because how many different 4 mers can we actually have in DNA? Well, we can have 4, because there are 4 letters, right, in the DNA alphabet, to the power of 4. since we have 4 mers. And this is actually 256. So here we only look at these 256 4 mers and count how many times we see each one of them in each contig. And the reason we have to be fairly short k-mers for this type of idea, because we need all contigs to contain virtually all of them, because we are looking at the frequencies, right? How often they occur. So we count these 4 mers for each contig, and I think if you go into the paper and read it in detail, you will also find they say that they only use canonical 4 mers. So it's not actually 156, it's actually 136 or something like that. It's not the half. It's not the half, because since k is even number, you have this palindrome sequences that makes it a little bit fiddly, I would say. So personally, I think I would have chosen 5 mers simply for that reason. But anyway, doesn't matter. Form a vector of such read counts and divide all values by the total sum. Actually, the last part here is not really stated anywhere, as at least I couldn't find it in that paper, that they actually divide by the sum of the total so that you have relative frequencies. I presume this is what they do because of some of the results they show, some of the distances we will see shortly, and also because if you don't do this, if you look at the actual read counts, then 2 contigs of different length will also be very different from each other, because there will be many more 4 mers in a long contig than in a short one. So it makes sense to divide by this total sum to get relative values. So I am pretty certain this is what they do, but they don't actually state this as far as I could see anywhere. Yeah, so you form a vector of this type, and then the elements must be in a fixed order. So this vector could, for instance, be something like this, where I have fixed the 4 mers in alphabetical order. It doesn't have to be that order, but some fixed ordering, right? So here we can see that this 4 mer, AAAA, has a value 0.01, meaning this occurs as 1% of all the 4 mers are this 4 mer, right? And here 0.3% of all the 4 mers is this one, right? And then 0.1% is this one, and so on. So you get these relative frequencies. And now if you sum up all these values, they sum to 1, right? That's the effect of this up here. So regardless of contig being short or long, these values are comparable, right? Because they are sort of fractions of the total number of k-mers, 4 mers. So this is the tetranucleotide frequencies, or relative frequencies actually. Okay, so how is the number of bins actually determined in this method? Let's go back to the paper here. And actually, I think if you scroll down past this part here and into this section here about initializing the algorithm, right? I think this is where it's described. A little bit hidden away, I would say. Remember that there are this 107 single copy genes, marker genes. And these are the important ones here, because it appears that, or at least the authors here claim that these 107 genes are typically single copy genes in 95% of all sequence bacteria. Meaning that if you find this gene in a bacteria, you always find it in one single copy only. Bacteria never have 2 or more copies of these genes here, they claim. At least 95% of the bacteria has it as a single copy. And this, of course, means that if we now find a number of copies of these genes, this number of copies is a proxy for the number of genomes, because we know that each genome has one each, right? If we believe in this statement here. And this is exactly how they do it as well. So they say that, let me see. Yeah, the median number of scaffolds containing each of the marker genes is identified. Of course, of these 107 marker genes, some of them, let's say some of them are found in 10 copies, and some in 11, and some in 9, right? So they will not come out exactly the same number of copies, all 107 of them. And then they take the median of this, right, as an estimate of the actual copy number. So we can conclude like this. We have the 107 single copy genes. We expect this to be found once and only once in every genome. If these are found in X copies, it indicates we have X genomes. That's reasonable, right? And then we find the copy number of all these 107, which is not all exactly equal to X. Some are a little bit larger, some a little bit smaller. And then we take the median of this to get our X, right? So this is how these 107 genes are utilized, the marker set. And remember, if you go back to my document, I wrote there a little bit that you can actually choose between using this 107 or a smaller set of 40. And you should use the 107 as long as you have sampled a metagenome, which is sort of a reasonable composition, meaning that the bacteria in there are probably the same bacteria we have in the databases, or at least something similar. But if you have sampled a very, very strange and different community, for instance, some soil or some water, sea floor sediments or something like that, which is probably containing a lot of new organisms that we haven't seen before, then you can replace this 107 with the 40 genes that are even more conserved, right, than these 107. But the idea is the same. Okay, what is meant by a Euclidean distance between tetranucleotide frequencies? Because this occurs also in the paper. If we scroll a little bit back again here, yeah, here it says that they compute what they call a Euclidean distance, right, between this tetranucleotide. This is this vector of tetranucleotide for one contig or scaffold 1, contig 1, S1, and the same for another contig, S2. So how is the Euclidean distance? Let me remind you, this is something you should actually know. So here I have the two tetranucleotide frequencies. So this is now for S1 contig, and this is the same for S2, right? And now you can see why it is so important that we have a fixed ordering here, because now this value here should be compared to this value here, and the same for the rest here. And what is actually the Euclidean distance between S1, S2, between these two vectors? Think of these two rows as two vectors, right? What is the distance between these two rows? Well, it's defined like this, the Euclidean distance. Right? You take, you let I here is now which of the columns you look at. So here we have I equals to 1, here I equals to 2, and so on. I equals to 3, so this is sort of a for loop, right? And so on. And there are 256 formares, right? So that's why I goes from 1 to 250. In each case, we just simply take this number minus this number, and we square it. And then we add to this the exactly same thing. We take this number minus this number squared again, right? So we have this summation here, right? We sum up the difference, square differences, and then we take the square root in the end. And this is normal distance, right? We call it the Euclidean distance, but this is how you measure distance in normal life. Actually, it's the length of the straight line between 2 points. And these are the coordinates of the points. So think of these as coordinates of points in a 256-dimensional space. And then you compute the distance like this. In R, we would compute it something like this. In one line of code, don't need any looping or anything, because in R you can subtract vectors from each other directly, and you will always get the element-wise differences, and then you square it and sum it, and then you take the square root after summing. So you can see this formula here is very easy to do in R. So this is the Euclidean distance, right? So if two rows here now have almost the same values, the distance becomes small, right? But if the values varies, if the first row has small values and then big values, and the second one has first big values and then small values, then the differences become big, right? So then the distance becomes big. So this is a measure of how similar these frequencies are, former by former. So if the idea is that if two contigs have approximately the same formers occurring frequently or infrequently, they are probably from the same genome. And this is a reasonable assumption. This is, you could say, an expansion of the GC content idea that I wrote a little bit about in my document. Okay. What is meant by this p-dist thing? Let me go back to my pointer. p-dist, and then we have to go into the paper again, I think, because first we compute this Euclidean distance between a pair of contigs, right? This could be principal between all pairs. And here we make use of these distances now in this formula here. And this is an important one. Probability based on distances that contig number 1 belongs to the same genome as contig number 2. This is how I would read this. Right? S1 belongs to the set, the genome where this contig also belongs to. So this is the probability that S1 and S2 comes from the same genome based on their distances that we computed up here. And what is this formula here? Actually, it's better to have a look at one of the figures that is here under additional information. And here it is. This is the figure. And let me explain what they have done here. First of all, they took some already sequenced genomes, and then they split these genomes into like contigs, right? We can just take a genome sequence and cut it into pieces, fairly long pieces though, as if they were contigs. And then they computed this Euclidean, they counted these former frequencies, right? Just like we saw now for each contig. And then they computed this Euclidean distance between the contigs from the same genome, and then made a histogram of all these distances. So here you can see the distances along the x-axis, and along here is how many contig pairs that falls into the different bins here or intervals, right? So they have pretty small intervals here, so the bars are pretty thin. And they did this for, I think it was million. Yeah, quite many contig pairs, right? You can see the numbers here are pretty big. And we can see that as long as you compare contigs from the same genome, you compare one contig from a genome to another contig from the same genome, that's what we see here, the distances are fairly small. Because they come from the same genome, they have approximately the same 4-mer frequencies. Over here at the B panel, you have exactly the same type of histogram, but these are now when you compare a contig from one genome to a contig from another genome. So here we have across different genomes, right? While here we are within the same genome, here we are between genomes. And then we can see the distances are much bigger. Can you see that? This is the histogram here. Few of them are down here, almost none of them are this small, right? But up here on quite big distances, we see many. Most of them here though. So here we have actually the density curves for these two histograms that we have in A and B, where blue is the one for this one and red is the one for this one. Actually, they have, it's not really the densities for the data. These are normal distributions, I think. For they have sort of fitted a normal distribution to both of them and then displayed that one instead, right? So you have one blue distribution here and a red one here. And the blue is for intragenome, right? Within genome. And the red is between genome, intergenome. And then the last panel here, which is actually this p-dist quantities. That's actually what we call the posterior probability based on these two densities. So how do we get the values of this black curve? Well, you do it like this. For one particular position on the x-axis here, you measure the height of the blue curve, and then you divide it by the sum of the height of the blue and the red. And that's exactly, if you go back to the formula here, this is the height of the blue curve in the numerator, and below here you see the sum of the height of the blue and the red. So this is how you interpret this black curve. You compute this directly from these red and blue over here. So we can see that here at very small distances, the blue curve is by far the highest, right? Lies at the highest level. So if you sum the blue and the red here, the red contributes with very little. So the sum is only a little bit higher than the blue, which means the blue is like 90% of the sum up here, right? And then the blue curve grows and the red curve also grows, but not as fast. So when we come right around here, we are at the top, right? Here we have the largest posterior probability, as we say, for the blue, right? But then as we go to larger distances, for instance here, they are just equally big, right? The blue, if you read the height of the blue curve here and the red curve, they are the same, which means the height of the blue divided by the sum of the two is exactly 1/2. So here you have 1/2. That is exactly here. So now we are, this is the sort of tipping point, you could say, right? If you are below here, it's more than 50% chance the distance is from within a genome. But if you are up here, the chance is less than 50% and much less, you see here, for being between two genomes. So when you compute the distance between, you have two new contigs, you don't know if they belong to the same genome or not. You compute the Euclidean distance, and if the distance falls in here, down here somewhere, you can say pretty certain that this is probably from the same genome, right? High probability. But if the distance is out here, the probability they are within the same genome is almost zero, right? This must be from different genomes then. So that's how these tetranucleotide distances are used to compute this here, p-dist actually. Probability that the two contigs come from the same genome based on their tetranucleotide frequencies. And the next is almost the same thing, but based on coverage instead. Similar probability based on coverage. And how is that idea? That's slightly different. Let's go back to and here we have the formula for coverage. And then they say we use directly the Poisson distribution. Notice the same sort of expression here, right? But now it's the same probability, or it's the probability of the two contigs being from the same genome based on coverage. And then we say, take the coverage for one of the genomes, one of the contigs, the coverage for contig S2, use that as the parameter in the Poisson distribution, and compute then the probability of the other coverage. Notice there is one right parenthesis lacking here. You can see it down here. It's actually correctly written. But so what does this mean? Let me show you in R. So let's have some coverage values here, X, right? And if we compute this density values of the Poisson distribution, we have done this before actually, and say that in contig S2 we have a coverage of, let's say, 50, right? Coverage 50 in S2 contig. Yeah, let me see. I want to have a blue curve here. And I want it a little bit fat as well. Oops. There it is. So this is the Poisson distribution when you have coverage 50, right? We can see the peak is at 50, and it is has some variance here. So if I change the lambda value, the expected value, for instance, to 70, it moves to 70, right? Here. Or if the coverage drops to 30, it moves down here, and you can see the variance shrinks as well. This is typical of the Poisson. The point is now that this value here that decides where the peak appears, this is now the coverage for the S2 contig. And then we take the coverage of the S1 contig, and let's say that's 20, right? So S2 has coverage 30, but S1 has coverage 20. What's the probability that these two are from the same genome? Well, then we go in here at 20 and up here, and then we read the probability here. So this is actually P-cob on this axis here now. Depending on where the S1 appears along this axis here, as long as S2 has a coverage of 30. And of course, if this is the coverage of S2, 70, then S1 has to be around 70 as well, right? In order to have similar enough coverage to be from the same genome. And we use the Poisson distribution directly. So if S2 has coverage 70 and S1 has coverage 20, then the probability is almost zero, right? And we can say, no way, these two can come from the same genome. So this is actually the idea of, of this P-cob here. Fairly straightforward, I would say. And then the very last thing is to understand this EM algorithm. That's rather a big topic. So let's just briefly look at it. And here we have it as a 5-step procedure. And first of all, it's this tetranucleotide frequencies, right, that we have seen now. Compute them. And then initialize the total number of genomes, n. Right? We saw how to find this capital N. It was this 107 single copy genes. So instead of X, as I called it, they call it capital N here. That's the number of genomes we think we have in this metagenome. And then each of these genomes must have a sort of a starting nucleotide frequency and also starting coverage level. And how do we actually find these ones? Well, then we have to go down to this section here again, initializing of the algorithm. Because remember, we looked at these 107 single copy marker genes and found this N, right, the copy number of them. And then they say here that the shortest marker gene that corresponds to the median number of bins, that's the capital N, right? Then we locate all the scaffolds or contigs where this harboring this shortest marker gene, and these are extracted. The tetranucleotide frequencies of these and also the coverage for these are used as starting values for the algorithm. So we compute the tetranucleotide frequencies and read coverages for these scaffolds, having this shortest gene only. And why only the shortest gene? It says here, the reason we use the shortest marker gene is that they are less likely to be split between two scaffolds. Yeah, it sounds like a good argument to me. So that means we now have sort of decided on the number of bins we are going to split the contigs into, and we also have computed a sort of a tetranucleotide frequency typical for each bin and a coverage typical for each bin. And then this probability here is computed, and notice that here we use the p-dist and the p-cov, right, in the numerator here, and in the denominator we just add up all these probabilities for all contigs. So we have again a sort of a relative value here, and this is then the probability that contig number j belongs to genome number I, right? And based on this, we assign now each contig to the genome that it has the highest probability of this. And once you've done that, you can compute new sort of representative frequencies and new representative coverages based on those contigs who were assigned to these different genomes, different bins, right? And then you go back here again and do this all over again with the new values of tetra and lambda for each bin. So actually step 3 and 4 is repeated until convergence. So you first estimate which bin do each contig belong to, and then you take these bins and compute new sort of representative frequencies and coverages for each contig, and then you go back here again and do the assignment again based on the new values, and then you compute new values based on the assignment. So this is like going back and forth, right? This EM algorithm, it's called expectation maximization. And finally it converges, or actually they have set an upper threshold. If you have iterated back and forth more than 50 times, you give up sort of, because it could happen that it doesn't really actually converge. It starts shifting at a very sort of stable position between two different states. Yeah, this is technical details. But that's the idea of the EM algorithm. So finally, you have these values here, you could say. These values here are the sort of the final output, I would say. So for each contig, you have a probability that it belongs to bin number I. And then you assign it to the bin where it has the highest probability. And they also say down here somewhere, this probability has to be, I think, more than 80%, right? 0.80. I think that was somewhere here. If it's less than 0.80, they call it unclassified, right? We couldn't determine which bin this config belongs to. It has to be more than 0.80. And in most cases, I think that's not a problem because it's sort of, yeah, unless you have very poor contigs then, and then of course it's impossible to know where they come from, but they are rubbish anyway, right? So that's it, I think, the max bin idea.